this particular thread should use this particular protection domain. And so I was sort of setting a thread local variable for the next allocation to happen. Alright, and then garbage collection obviously just has access to everything, so we were using a stop the world garbage collection. So everything stopped except the garbage collection thread had access to everything, cleaned it up, and then the program threads, mutator threads, continued normally after that. Alright, and then we merged our custom signal handler with the Java virtual machine signal handler, and we also they also had a mechanism to propagate memory errors. For example, they do null checking using signal handlers. So we extended that to actually be able to throw a Java exception if a particular thread tried to access memory that it didn't have. So your program won't crash hard, it'll just throw a runtime exception at that point. So, you know, how do we measure, you know, just at least just one measure here of performance. So here's a slightly simpler example than the browser example. Just imagine you've got this master worker type model, which is pretty common in embarrassingly parallel applications in scientific computing or elsewhere, where you've got a master who's filling up and controlling some queue of items that need to be processed, and then you've got one or more workers, you know, operating on different threads that take things out of the queue, do some sort of work on them, and then put the results back into the queue. So how would we structure protection domains for this? So we've got, you know, the master private state, which the workers should need to know nothing about. All they care about is doing their work. You've got the queue data, so the master is the only one who's allowed to actually put items into this work queue, modify things in the work queue, the actual things that need to be done. So the different workers can't manipulate, you know, what its other worker is going to be doing or what the master wanted it to do. But it does need to have write access to the queue control area, what's actually on the queue, because obviously a worker will have to take something off the queue, so it can't be completely isolated. So we separated these out. Alright, and then the way we modeled it for a micro benchmark is we just had 32 megabytes of data, and we varied the item size. So each item was different sizes ranging from 4 kilobytes to I think 4 megabytes, you know, however number of items it took up to fill 32 megabytes. And we wanted this to be a memory intensive bandwidth rather than CPU intensive. So we just, the only thing that the worker does when it consumes an item is it copies it and then it sums up everything inside of that just to make sure that we've actually touched everything. The JVM hasn't optimized that out. So here we've plotted the original Jikes RVM virtual machine unmodified in blue, and then we've got our modified Ribbon virtual machine running with our custom Ribbon, you know, the code enhanced with our ribbons, plotted at 99% confidence intervals, and the confidence intervals always overlap. So essentially you've got no noticeable performance impact, which of course we would expect because the only overhead you're actually hitting is the first time, you know, the ribbon accesses a ribbon accesses a page. You've got that extra signal handler, but after that, you know, in this example, it's very stable, and there's no extra signal handlers being called, and so there's no overhead. So it just sort of validates that, you know, there wasn't any funny behavior introduced by our approach. And this is the same test here. It's just showing throughput in megabytes per second. So interestingly enough, you know, as you would expect, smaller the queue item size, faster the number of items you can process per second. As items get larger, you know, you're doing more work actually doing memory-intensive operations rather than manipulating the queue, and so your memory bandwidth goes up. All right, so just to conclude here, we've covered our proposed idea of ribbons to provide this sort of access control mechanism over the heap that's also works on existing standard hardware and is efficient. We also believe this is the first language extension where you have these type protection domains that are instantiated at runtime, so you've got this flexible dynamic memory segmentation model. We've never seen the inject privilege modeled explicitly before in the language, and also this idea of adaptable isolation levels. And finally, this is ongoing work, so we are working on a kernel extension so we can actually provide security for native applications, move all of that metadata into the kernel, and also get those performance optimizations we were talking about, get the kernel scheduler aware of the ribbons. Another important, that we feel is important for securing existing applications is being able for the same thread to securely switch which ribbon it's currently executing on. So for example, Firefox, at least in 3.5, is single-threaded mostly. So it would have a hard time. You'd have to re-architect a fair amount of the code just to enjoy the benefits of ribbons. And so instead, we're investigating techniques. How do we securely provide a mechanism to switch into a more restrictive ribbon and know when it's safe to actually switch back out without being manipulated? And so one possible technique that we're looking at for this is module boundaries. So when you load the shared object for the Flash player, for example, it's going to have its own different address space. And so you can take advantage of that, of those known boundaries, and unmap those text segments so that when you do the switch, you can automatically switch ribbons, for example. And we're just investigating the details. How do you, securely switch back? Do you have to have, you probably have to have different stacks for each of the ribbons, and if you do, when you make a call between them, how do you know how much of the stack to copy in order to get the arguments for the cross-ribbon function call to come across correctly on the stack? And the same thing about functions that return data. There's also the complicating factor of callbacks. When the Flash plugin, if it needs to manipulate the DOM or tell the browser open a pop-up or whatever, how does it call back out of its isolated ribbon and actually execute that callback inside of a different ribbon and then switch back? And so we're looking at how to structure these calls in a secure fashion, but yet isn't too intrusive on actual code. So that ends the presentation. So be very happy if there's any questions. Patrick?
Can you comment more on the symmetry or lack thereof between grant and required permissions?
Yeah, so I guess one common question is why do you actually need a grant and require? And that's more of a function of the RibbonJ language. So our actual implementation only understands the grant ability. You're just granting from source to the target. And the key thing is when you're constructing a new ribbon, right now the initial protection domain is constructed, and then you grant all of the relevant permissions on that domain, and then you make a call to put that new protection domain into isolation with the given isolation mode. So at that point, that's when the restrictions on the grant operations take into effect. You're sort of locking it down at that point. Any other questions or ideas for application, thoughts? Any skeptics?
You say that you unmap these pages when you're not in a particular library. You also unmap them like on a timer interrupt or whatever, when you're just, not when you're returning from the library, but when you're just switched out incidentally?
When you're switched out incidentally, like just switching to another process, I think you would just leave things the way that they are, because when you came back, it would restore your same page table entries, and then you'd still be operating within that same ribbon, but of course you'd still be at the same point in the code. Your instruction pointer would be the same. So we haven't yet encountered a place where we need to do that on a timer yet, at least. So, yeah, I guess if there's no further questions, we'll just end here then.